A field-programmable gate array is an integrated circuit designed to be configured by a customer or a designer after manufacturing hence field-programmable. The FPGA configuration is generally specified using a hardware description language, similar to that used for an application-specific integrated circuit. Contemporary FPGAs have large resources of logic gates and RAM blocks to implement complex digital computations. As FPGA designs employ very fast IOs and bidirectional data buses, it becomes a challenge to verify correct timing of valid data within setup time and hold time. Floor planning enables resources allocation within FPGA to meet these time constraints. FPGAs can be used to implement any logical function that an ASIC could perform. The ability to update the functionality after shipping, partial reconfiguration of a portion of the design, and the low non-recurring engineering costs relative to an ASIC design, offer advantages for many applications. FPGAs contain programmable logic components called logic blocks, and a hierarchy of reconfigurable interconnects that allow the blocks to be wired together somewhat like many logic gates that can be interwired in different configurations. Logic blocks can be configured to perform complex combinational functions, or merely simple logic gates like AND and XOR. In most FPGAs, the logic blocks also include memory elements, which may be simple flip-flops or more complete blocks of memory. Some FPGAs have analog features in addition to digital functions. The most common analog feature is programmable slew rate and drive strength on each output pin, allowing the engineer to set slow rates on lightly loaded pins that would otherwise ring unacceptably, and to set stronger, faster rates on heavily loaded pins on high-speed channels that would otherwise run too slowly. Another relatively common analog feature is differential comparators on input pins designed to be connected to differential signaling channels. A few mixed-signal FPGAs have integrated peripheral analog-to-digital converters and digital-to-analog converters with analog signal conditioning blocks, allowing them to operate as a system on a chip. Such devices blur the line between an FPGA, which carries digital ones and zeros on its internal programmable interconnect fabric, and field-programmable analog array, which carries analog values on its internal programmable interconnect fabric. History: the FPGA industry sprouted from programmable read-only memory and programmable logic devices. PROMs and PLDs both had the option of being programmed in batches in a factory or in the field. However, programmable logic was hardwired between logic gates. In the late 1980s, the Naval Surface Warfare Department funded an experiment proposed by Steve Kesselman to develop a computer that would implement 600,000 reprogrammable gates. Kesselman was successful and a patent related to the system was issued in 1992. Some of the industry's foundational concepts and technologies for programmable logic arrays, gates, and logic blocks are founded in patents awarded to David W. Page and Lou Werner Peterson in 1985. Xilinx co-founders Ross Freeman and Bernard van der Schmidt invented the first commercially viable field-programmable gate array in 1985, the XC2064. The XC2064 had programmable gates and programmable interconnects between gates, the beginnings of a new technology and market. The XC2064 had 64 configurable logic blocks, with 2 3-input lookup tables. More than 20 years later, Freeman was entered into the National Inventors Hall of Fame for his invention. Xilinx continued unchallenged and quickly grew from 1985 to the mid-1990s, when competitors sprouted up, eroding significant market share. By 1993, Actor was serving about 18% of the market. The 1990s were an explosive period of time for FPGAs, both in sophistication and the volume of production. In the early 1990s, FPGAs were primarily used in telecommunications and networking. By the end of the decade, FPGAs found their way into consumer, automotive, and industrial applications. Modern developments: a recent trend has been to take the coarse-grained architectural approach a step further by combining the logic blocks and interconnects of traditional FPGAs with embedded microprocessors and related peripherals to form a complete system on a programmable chip. This work mirrors the architecture by Ron Perlov and Hannah Potash of Burroughs Advanced Systems Group, which combined a reconfigurable CPU architecture on a single chip called the SB24. That work was done in 1982. Examples of such hybrid technologies can be found in the Xilinx Sync-7000 all-programmable SoC, which includes a 1.0 GHz dual-core ARM Cortex-A9 MPCORE processor embedded within the FPGA's logic fabric, or in the Altair 5 FPGA, which includes an 800 MHz dual-core ARM Cortex-A9 MPCORE. The Atmel FPS-LIC is another such device, which uses an AVR processor in combination with Atmel's programmable logic architecture. The Actel Smart Fusion devices incorporate an ARM Cortex-M3 hard processor core and analog peripherals such as a multi-channel ADC and DACs to their flash-based FPGA fabric. In 2010, Xilinx Incorporated introduced the first all-programmable system-on-a-chip branded Sync-7000 that fused features of an ARM high-end microcontroller with an FPGA fabric to make FPGAs easier for embedded designers to use. By incorporating the ARM processor-based platform into a 28nm FPGA family, the extensible processing platform enables system architects and embedded software developers to apply a combination of serial and parallel processing to their embedded system designs, for which the general trend has been to progressively increasing complexity. The high level of integration helps to reduce power consumption and dissipation, and the reduced parts count versus using an FPGA with a separate CPU chip leads to a lower parts cost, a smaller system, and higher reliability, since most failures in modern electronics occur on PCBs and the connections between chips instead of within the chips themselves. An alternate approach to using hard macroprocessors is to make use of soft processor cores that are implemented within the FPGA logic. Nios 2, Microblaze and Mico32 are examples of popular soft-core processors. As previously mentioned, many modern FPGAs have the ability to be reprogrammed at runtime, and this is leading to the idea of reconfigurable computing or reconfigurable systems, or CPUs that reconfigure themselves to suit the task at hand. Additionally, new, non-FPGA architectures are beginning to emerge. Software configurable microprocessors such as the Stretch S5000 adopt a hybrid approach by providing an array of processor cores and FPGA-like programmable cores on the same chip. Gates, 1982, 8192 Gates, Burroughs Advanced Systems Group, integrated into the S-type 24-bit processor for reprogrammable I/O, 1987, 9000 Gates, Xilinx, 1992, 600,000, Naval Surface Warfare Department, early 2000s, millions, market size, 1985, first commercial FPGA Xilinx XC2064, 1987, $14 million, a Permil 1993, $385 million, 2005, $1.9 billion, 2010 estimates, $2.75 billion, design starts, 2005. 80,000, 2008, 90,000, FPGA comparisons. Historically, FPGAs have been slower, less energy efficient and generally achieved less functionality than their fixed ASIC counterparts. An older study had shown that designs implemented on FPGAs need on average 40 times as much area, draw 12 times as much dynamic power, and run at 1/3 the speed of corresponding ASIC implementations. More recently, FPGAs such as the Xilinx Vertex 7 or the Ultra Stratix 5 have come to rival corresponding ASIC and ASSP solutions by providing significantly reduced power, increased speed, lower materials cost, minimal implementation real estate, and increased possibilities for reconfiguration on the fly. Where previously a design may have included 6 to 10 ASICs, the same design can now be achieved using only one FPGA. Advantages of FPGAs include the ability to reprogram in the field to fix bugs, and may include a shorter time to market and lower non-recurring engineering costs. Vendors can also take a middle road by developing their hardware on ordinary FPGAs, but manufacture their final version as an ASIC so that it can no longer be modified after the design has been committed. Xilinx claims that several market and technology dynamics are changing the ASIC FPGA paradigm. Integrated circuit costs are rising aggressively, ASIC complexity has lengthened development time, R&D resources and headcount are decreasing, revenue losses for slow time to market are increasing, financial constraints in a poor economy are driving low-cost technologies. These trends make FPGAs a better alternative than ASICs for a larger number of higher volume applications than they have been historically used for, to which the company attributes the growing number of FPGA design starts. Some FPGAs have the capability of partial reconfiguration that lets one portion of the device be reprogrammed while other portions continue running. Complex programmable logic devices. The primary differences between CPLDs and FPGAs are architectural. A CPLD has a somewhat restrictive structure consisting of one or more programmable sum of products logic arrays feeding a relatively small number of clocked registers. The result of this is less flexibility, with the advantage of more predictable timing delays and a higher logic to interconnect ratio. The FPGA architectures, on the other hand, are dominated by interconnect. This makes them far more flexible but also far more complex to design for. In practice, the distinction between FPGAs and CPLDs is often one of size, as FPGAs are usually much larger in terms of resources than CPLDs. Typically only FPGAs contain more complex embedded functions such as adders, multipliers, memory, and surds. Another common distinction is that CPLDs contain embedded flash to store their configuration while FPGAs usually, but not always, require an external non-volatile memory. Security considerations. With respect to security, FPGAs have both advantages and disadvantages as compared to ASICs or secure microprocessors. FPGA's flexibility makes malicious modifications during fabrication a lower risk. Previously, for many FPGAs, the design bitstream is exposed while the FPGA loads it from external memory. All major FPGA vendors now offer a spectrum of security solutions to designers such as bitstream encryption and authentication. For example, Ultra and Xilinx offer AES encryption for bitstreams stored in an external flash memory. FPGAs that store their configuration internally in non-volatile flash memory, such as Microsemis Pro ASIC 3 or Lattice's XP2 programmable devices, do not expose the bitstream and do not need encryption. In addition, flash memory for a lookup table provides single-event upset protection for space applications. Applications. Technically speaking, an FPGA can be used to solve any problem which is computable. This is trivially proven by the fact FPGA can be used to implement a soft microprocessor. Their advantage lies in that they're sometimes significantly faster for some applications due to their parallel nature and optimality in terms of the number of gates used for a certain process. Specific applications of FPGAs include digital signal processing, software-defined radio, ASIC prototyping, medical imaging, computer vision, speech recognition, cryptography, bioinformatics, computer hardware emulation, radio astronomy, metal detection and a growing range of other areas. FPGAs originally began as competitors to CPLDs and competed in a similar space, that of glue logic for PCBs. As their size, capabilities, and speed increased, they began to take over larger and larger functions to the state where some are now marketed as full systems on chips. Particularly with the introduction of dedicated multipliers into FPGA architectures in the late 1990s, applications which had traditionally been the sole reserve of DSPs began to incorporate FPGAs instead. Traditionally, FPGAs have been reserved for specific vertical applications where the volume of production is small. For these low-volume applications, the premium that companies pay in hardware costs per unit for a programmable chip is more affordable than the development resources spent on creating an ASIC for a low-volume application. Today, new cost and performance dynamics have broadened the range of viable applications. Common FPGA applications. Architecture. The most common FPGA architecture consists of an array of logic blocks, I/O pads, and routing channels. Generally, all the routing channels have the same width. Multiple I/O pads may fit into the height of one row or the width of one column in the array. An application circuit must be mapped into an FPGA with adequate resources. While the number of CLBs, labs and I/Os required is easily determined from the design, the number of routing tracks needed may vary considerably even among designs with the same amount of logic. For example, a crossbar switch requires much more routing than a systolic array with the same gate count. Since unused routing tracks increase the cost of the part without providing any benefit, FPGA manufacturers try to provide just enough tracks so that most designs that will fit in terms of lookup tables and I/Os can be routed. This is determined by estimates such as those derived from Rent's rule or by experiments with existing designs. In general, a logic block consists of a few logical cells. A typical cell consists of a 4-input LUT, a full adder and a D-type flip-flop, as shown below. The LUTs are in this figure split into two 3-input LUTs. In normal mode those are combined into a 4-input LUT through the left mu. In arithmetic mode, their outputs are fed to the FA. The selection of mode is programmed into the middle multiplexer. The output can be either synchronous or asynchronous, depending on the programming of the mu to the right, in the figure example. In practice, entire or parts of the FA are put as functions into the LUTs in order to save space. ALMs and slices usually contains 2 or 4 structures similar to the example figure, with some shared signals. CLB's labs typically contains a few ARMS slices. In recent years, manufacturers have started moving to 6-input LUTs in their high-performance parts, claiming increased performance. Since clock signals are normally routed via special-purpose dedicated routing networks in commercial FPGAs, they and other signals are separately managed. For this example architecture, the locations of the FPGA logic block pins are shown to the right. Each input is accessible from one side of the logic block, while the output pin can connect to routing wires in both the channel to the right and the channel below the logic block. Each logic block output pin can connect to any of the wiring segments in the channels adjacent to it. Similarly, an I/O pad can connect to any one of the wiring segments in the channel adjacent to it. For example, an I/O pad at the top of the chip can connect to any of the W wires in the horizontal channel immediately below it. Generally, the FPGA routing is unsegmented. That is, each wiring segment spans only one logic block before it terminates in a switch box. By turning on some of the programmable switches within a switch box, longer paths can be constructed. For higher speed interconnect, some FPGA architectures use longer routing lines that span multiple logic blocks. Whenever a vertical and a horizontal channel intersect, there is a switch box. In this architecture, when a wire enters a switch box, there are 3 programmable switches that allow it to connect to 3 other wires and adjacent channel segments. The pattern, or topology, of switches used in this architecture is the planar or domain-based switch box topology. In this switch box topology, a wire in track number 1 connects only to wires in track number 1 and adjacent channel segments, wires in track number 2 connect only to other wires in track number 2 and so on. The figure on the right illustrates the connections in a switch box. Modern FPGA families expand upon the above capabilities to include higher-level functionality fixed in their silicon. Having these common functions embedded into the silicon reduces the area required and gives those functions increased speed compared to building them from primitives. Examples of these include multipliers, generic DSP blocks, embedded processors, high-speed I/O logic and embedded memories. FPGAs are also widely used for systems validation including pre-silicon validation, post-silicon validation, and firmware development. This allows chip companies to validate their design before the chip is produced in the factory, reducing the time to market. To shrink the size and power consumption of FPGAs, vendors such as Tabula and Xilinx have introduced new 3D or stacked architectures. Following the introduction of its 28nm7 series FPGAs, Xilinx revealed that several of the highest density parts in those FPGA product lines will be constructed using multiple dies in one package, employing technology developed for 3D construction and stacked die assemblies. The technology stacks several active FPGA dies side by side on a silicon interposer, a single piece of silicon that carries passive interconnect. FPGA design and programming. To define the behavior of the FPGA, the user provides a hardware description language or a schematic design. The HDL form is more suited to work with large structures because it's possible to just specify them numerically rather than having to draw every piece by hand. However, schematic entry can allow for easier visualization of a design. Then, using an electronic design automation tool, a technology map netlist is generated. The netlist can then be fitted to the actual FPGA architecture using a process called place and route, usually performed by the FPGA company's proprietary place and route software. The user will validate the map, place and route results via timing analysis, simulation, and other verification methodologies. Once the design and validation process is complete, the binary file generated is used to configure the FPGA. This file is transferred to the FPGA CPLD via a serial interface or to an external memory device like an EEPROM. The most common HDLs are VHDL and Verilog, although in an attempt to reduce the complexity of designing in HDLs, which have been compared to the equivalent of assembly languages, there are moves to raise the abstraction level through the introduction of alternative languages. National Instruments LabVIEW graphical programming language has an FPGA add-in module available to target and program FPGA hardware. To simplify the design of complex systems in FPGAs, there exist libraries of predefined complex functions and circuits that have been tested and optimized to speed up the design process. These predefined circuits are commonly called IP cores, and are available from FPGA vendors and third-party IP suppliers. Other predefined circuits are available from developer communities such as open cores, and other sources. In a typical design flow, an FPGA application developer will simulate the design at multiple stages throughout the design process. Initially, the RTL description in VHDL or Verilog is simulated by creating test benches to simulate the system and observe results. Then, after the synthesis engine has mapped the design to a netlist, the netlist is translated to a gate-level description where simulation is repeated to confirm the synthesis proceeded without errors. Finally, the design is laid out in the FPGA, at which point propagation delays can be added and the simulation run again with these values back annotated onto the netlist. Basic process technology types, SRAM, based on static memory technology. In-system programmable and reprogrammable. Requires external boot devices. CMOS. Currently in use. Fuse, one-time programmable. Bipolar. Obsolete. Antifuse, one-time programmable. CMOS, PROM, programmable read-only memory technology. One-time programmable because of plastic packaging. Obsolete. EPROM, erasable programmable read-only memory technology. One-time programmable but with window, can be erased with ultraviolet light. CMOS. Obsolete. EEPROM, electrically erasable programmable read-only memory technology. Can be erased, even in plastic packages. Some but not all EEPROM devices can be in-system programmed. CMOS. Flash, flash erase EPROM technology. Can be erased, even in plastic packages. Some but not all flash devices can be in-system programmed. Usually, a flash cell is smaller than an equivalent EEPROM cell and is therefore less expensive to manufacture. CMOS. Major manufacturers, Xilinx and Altera are the current FPGA market leaders and long-time industry rivals. Together, they control over 80% of the market. Both Xilinx and Altera provide free Windows and Linux design software which provides limited sets of devices. Other competitors include Lattice Semiconductor, Actel, Silicon Blue Technologies, Acronix, and QuickLogic. In March 2010, Tabula announced their FPGA technology that uses time-multiplexed logic and interconnect that claims potential cost savings for high-density applications. See also. References. Further reading, Sadrzinski, Hartmut F.W. Wu, Gina 1. Applications of field-programmable gate arrays in scientific research. Taylor and Francis. ISBN A978-1-4398-4133-4. Worth, Niklaus. Digital Circuit Design and Introduction Textbook. Springer. ISBN A3-540-58577 EXA. External links. University of North Carolina at Charlotte's Reconfigurable Computing Laboratory, Vaughan Betts's FPGA architecture page, tutorials and examples on FPGAs. What is an FPGA? On YouTube.